Hi friends, here is Lucas. This video contains a free module of my course Kotlin Coroutines and Flow for Android development. You can find the link in the description to get the course for a nice discount. I think a lot of people are really excited now, because in this module we are now going to learn about the second big topic of this course, and this one is about Kotlin Flow. Flows are based on coroutines, and now that you have a solid understanding about them, you are ready to learn about flows and how to make your apps more reactive. If you have jumped directly to this section though and skipped the coroutines part, well, that's also no problem. I will always refer to lectures of the coroutines part whenever I talk about a coroutine related topic in the flow part. So you can jump back to the coroutine part in order to learn more about this coroutine related topic, if you need to. As this is a very practical course, we are going to jump into Android Studio really fast in order to implement a first real-world feature, a stock live tracking feature, which receives new stock data from a flow every couple of seconds and makes heavy usage of the concepts that you learn in this module. The concepts that you will learn are what exactly is a flow, what is reactive programming, how to create flows with flow builders, how to apply operators on flows, and there are 3 different types of operators. First, lifecycle operators, second, terminal operators, and third, intermediate operators. By the end of this module, you will have a solid understanding about when you should use a flow and how to construct and consume flows in real applications. So without further ado, let's dive right into this module. Let's start this section with the question, what is a flow? A flow is a type in the Kotlin coroutine library which was introduced in 2019. A flow represents a stream of values that are computed asynchronously. An even shorter description would be that a flow is simply an asynchronous data stream. But what is an asynchronous data stream? The best way of learning is by doing. So let's try to create such an asynchronous data stream. Therefore, let's take this code example. I created a new package called flow in the playground package, and in there I created a new file called one-return single item, and I already prepared some code in there. If you can't see this file in your project, please make sure to pull the latest changes of your current branch. I created the modules about flow later than the ones about coroutines, so it could be the case that you need to pull the latest changes. Of course, if you chose to use the coroutines course empty branch, you won't see this file, as on this branch you can code alongside with me and create those files by yourself. But on the other branches, like the coroutine course complete branch or the coroutine course empty exercises branch, as well as on the master branch, you should see this file now. Let's talk about this code now. It should be familiar to you if you have watched section 8 in the coroutines part of this course, which was about background processing. In the main function, we call the calculate factorial of function, which is simply the function below, and then after we have calculated the factorial, we print it out. The calculate factorial of function returns a single big integer value, and in this function I added a thread.sleep call in order to simulate a longer running calculation. When we now run this code, then you can see on the right that a single line is printed out, basically just the result that we got from the calculate factorial of function. So right now, the calculate factorial of function returns only a single value. Our goal now is to convert this function, which as of right now returns only a single value, the final result, into an asynchronous data stream that not only returns the final result, but also all intermediate results. So a data stream always returns multiple values. Therefore, let's simply copy this file and create a new file called toReturnList. We now want to modify the calculate factorial of function in a way that it doesn't only return a single value, but a list of values. Therefore, let's change the return type from big integer to a list of big integers. To build a list, we can use the buildList builder function. Now we can use the add function to add new values to the list. Now we don't need the return statement anymore. In the main function, since we now get a list, we now want to use for each on this list. And for each value of the list, we want to use the print with time passed function to print out a message in combination with the time that passed since we started this program. This print with time passed function is a function that I recently added to the utils folder in the playground package. So let's simply print out the current item, and additionally we have to provide the start time to the print with time passed function. We simply define the start time at the beginning of the main function and assign it to system.currentTimeMillis. Now we can remove the second print statement. And we also don't need this result property anymore. If we now execute this code, as you can see, we are now not only getting a single value, but 5 values. At the beginning of the line in the console output, you can see how much time already passed since starting this program. And as you can see, all of these values were returned at exactly the same time. So we basically received all of the intermediate results at the same time at the end. So do we have a data stream here already? I would say no, because in a data stream, the data is received continuously, bit by bit, and not all at once, like we have it here. So let's fix this. But how? Well, we can use a sequence for that. Sequences allow us to lazily compute values. Therefore, let's again copy the current file and create a new one that we call 3sequences. Now we want to return a sequence, and therefore let's change the return type from list to sequence. To build a sequence, we can use the sequence builder. In sequences, we have to use yield instead of add. The code in the main function stays exactly the same. And if we now run this code, you can see that the intermediate results are not received together at the same time at the end, but at the time they are calculated. So after 23 milliseconds, after 36 milliseconds, after 47 milliseconds, and so on. So now we actually have a data stream, because the data is received continuously instead of only once in the end. However, this data stream is not yet asynchronous, but synchronous. This means that the call to for each in the main function is blocking our main thread. If we add a print statement after the for each statement in the main function and execute the code, you can see that this new print statement is only outputted after all the values from the sequence were received. So our main thread can only do work again once we have received all the values of the sequence. This means that the main thread is blocked as long as we are waiting for items of the sequence. So lazy sequences that perform expensive calculations should not be used, for example, on the Android main thread, because they could freeze the UI. The big limitation of sequences is that we cannot call suspend functions from within them. So we can't, for instance, call delay instead of thread.sleep in our sequences, or we also can't use with context, for example, to change the dispatcher. So sequences are always blocking a thread, but what we want to have is that only a coroutine is suspended. So how can we achieve this? How can we get an actual asynchronous data stream where we don't block the main thread? I think you guessed it, we have to return a, wait for it, Kotlin Flow. Therefore, let's copy this file once again, and the new file we call for flow. Our function should now return a flow. So let's change the return type from sequence to flow. The flow type and its functions are contained in the Kotlin X coroutines library that we already have included. So we don't need to add an additional dependency to our project. Now, instead of the sequence builder, we can simply use the flow builder. Of course, you will learn all about flow builders later in this section. In the flow builder, we can now call suspend functions. So let's now replace the call to thread.sleep with delay. As you can see, Flow fully supports coroutines. Instead of yield, we now have to use emit to return new values from the flow. Let's also add the flow on operator to the flow and pass the default dispatcher so that the calculation is executed on a background thread. Of course, you will learn all the details of this operator in a later section when we talk about concurrent flows. In the main function, in order to receive values from the flow, we now have to use collect on the flow. Of course, we will talk more about the collect operator later. But for now, all you need to know is that using collect on a flow is similar to using for each on collections. However, we get a compilation error. And this is because collect is a suspend function and we have to use collect from either a coroutine or another suspend function. Therefore, let's use the run blocking coroutine builder for our main function. And then let's launch a new coroutine in which we collect the items from the calculation. When we now run this main function here, you can see that we again receive the values continuously. So after 51 milliseconds, 63 milliseconds, and so on. But what's different now is that ready for more work, so the print statement that we had at the end of the main function is immediately printed out. So here, the main thread isn't blocked anymore, while the factorial intermediate results are calculated. So now we have finally reached our goal of converting the calculate factorial of function from a function that returns a single value into an asynchronous data stream. I hope that you now have a basic idea what a flow actually is and how a stream of data that is computed asynchronously looks like. Let's now recap what we did in this lecture. In the beginning, we simply had the calculate factorial of function that returned a big integer value. So we received a single value once. And while the calculation was running, the main thread was blocked. Then we changed the function and returned a list of big integers with all the intermediate results. This way, we received multiple values, but also only once when the whole calculation was completed. Again, we blocked the main thread. After that, we used a sequence. And this helped us to receive the intermediate results as soon as they were calculated. So we received the values continuously instead of only once. However, we still blocked the main thread. So the values were not calculated asynchronously, but synchronously. Finally, we arrived at using a flow, with which we were able to continuously receive data without blocking the main thread. We created our first asynchronous data stream. Nice! Now, the last thing that I want to talk about in this lecture is the difference between a suspend function and a function that returns a flow. In suspend functions, we can perform asynchronous operations and then return a single value. In regular functions that return a flow, the flow itself can also perform asynchronous operations. However, instead of returning only a single value, a flow can return, or in flow terminology, emit, multiple values. Kotlin Flow implements the reactive stream specification. By using flows, we follow a programming paradigm that is called reactive programming. In this short lecture, we are now going to take a look at the differences of reactive programming and conventional imperative programming. The foundation of reactive programming is the observer pattern, in which software components can observe other components, receive state changes, and react accordingly to these changes. Libraries like RxJava or native frameworks like Kotlin Flow extend the idea of the observer pattern by adding some useful operators for data processing and threading on top of it. Actually, we already develop in a reactive style since the beginning of this course. Why? Well, because we are using LiveData. LiveData is a data holder that can be observed, and whenever there is a new state, we can react to it. In our activities, we observe the UI state, the LiveData properties of the view models, and then render the new UI state on the screen whenever there is a change. With Flow, however, we can also make other layers of our apps reactive as well. For example, the room persistence library, which is a part of the Android Jetpack library collection, allows us to expose database tables as flows. This enables other components to subscribe to that flow in order to get notified whenever the data in the database changes. We could implement our app in such a way that whenever the data in the database changes, the UI is updated immediately. On the other hand, if our room database would expose a simple suspend function, then we would need to follow the conventional imperative approach. Therefore, we would need to proactively check for data changes. This has obvious drawbacks, like for instance bad responsiveness because of the possible delay between data changes in the database and UI changes. Nonetheless, there are also some disadvantages, by developing apps with a reactive programming paradigm. Probably the biggest one is that we need to learn new concepts and operators. For many developers, these new concepts and operators are hard to understand, which means that also the resulting code will be more complex and therefore harder to read. Yet, be brave. I'm giving my best to teach you all of the complex concepts that come with reactive programming with Kotlin Flow in a simple and approachable way. My goal is that a lot of students are going to master and deeply understand this topic and then are able to properly use flows in production apps. Let's achieve this together. As you already know, this course is very practical. Therefore, let's implement our first real-world Android use case that uses a flow. Our goal of the first use case is to build a stock price live ticker feature. As you can see on this screenshot, the feature should display the live stock prices of the biggest publicly owned companies in the world, like Apple, Saudi Aramco, or Microsoft. The stock data is retrieved by periodically calling a mocked endpoint. Within our app, we will extract this data fetching logic into a separate component, the DataSource, and this DataSource will expose a flow of stocks. In the view model of this use case, we can then observe this flow in order to get updated whenever we have new data about the stock prices. Whenever we receive new data, we are going to update the UI state of the LiveData properties in the view model. The activity observes the UI state LiveData property and renders new stock data in the UI. And that's what we want to achieve. So let's now start with the implementation. As you can see in the project view on the left of the IDE, I already prepared the necessary infrastructure code for the use case. When we now launch the app, you can see that we now have a flow use cases menu item in the main list. And we also have our first use case in the sublist. Let's now quickly go through the necessary infrastructure code for our new stock prices live tracking feature. I created a new package in the use cases package, and in there is a new mock package. For our flow use cases, we will use a different mock API than the one for the coroutines use cases. This new API is specified in the flow mock API.kt file. As you can see, we have a new endpoint there, and this one is called getCurrentStockPrices, which returns the list of stocks and their current price. The other file in the mock package is called flowmockdata.kt, and it contains the data that can be returned from our mock API. In there, we have the model definitions for a stock, currency, and the price trend. The stock data class has quite some properties, but for our first example, only the name and the current price are relevant. I also created a new package for use case number 1. In there is another file that is relevant for our mock API behavior, and this is the one that is called mockAPIBehavior.kt. Let's have a look in there. So here we define that for every call to the current stock prices endpoint, we return the result of the function fake current stock prices. This function is defined in flow mockdata.kt file. We have seen it before. And this function basically first reads the stock data and then generates a random new stock price. In order to get real stock prices, I added a new file stockdata.csv into the assets folder. And in there you can see we get all the data for our stocks. And in the flow mock data file in the fake current stock prices function, you can see that we first read this current CSV file and then we generate a random new price for the stock, so that for every network request to the mock API, we basically get a new stock price. All right, so that's how the mock API is working. Let's now take a look into the activity of our use case. It is not really necessary for you to understand every detail of the activity. All the flow-related logic will be located either in the view model or in components with which the view model interacts. However, it doesn't hurt to know the basics of what's happening in the activity. So the activity basically just observes the LiveData property called current stock price asLiveData of the view model and renders every received UI state on the screen. When we take a look at the UI state sealed class hierarchy, it should also look very familiar to other use cases. So here we have a loading UI state, a success UI state that contains the stock list and its current prices. And also here we have the error UI state. So let's now go back to the activity and have a look into the render function. And here you can see whenever we get a new UI state and call the render function, when this UI state is basically of the loading state, then we only show the progress bar and hide the recycler view, which contains the list of stocks. If we get a success UI state, then we show the recycler view, and we also update the last update time text field with the current time. We set the stock data for the adapter, and we hide the progress bar. For error UI states, we simply show a toast message with the error message, and also we hide the progress bar. All right, we have now covered all the necessary infrastructure code in order to implement our stock price live ticker feature. So let's open up the view model of the use case. And as you can see, there's the current stock price as LiveData property. And this is the one we need to implement. As mentioned before, we can set different UI states here, and the activity observes this property and then renders the received UI state onto the screen. But before we implement this property, let's first take a look at the constructor of this view model. It has a stock price data source as a single dependency. As you know, we want to get the most recent stock price from this data source, but we have to implement this data source first. So let's jump into its implementation. As you can see, the stock price data source is an interface. This is important for our view model so that we can depend on an interface of the data source instead of a concrete implementation, because then we can use a fake implementation of the data source in our tests. Below the interface, you can see the network stock price data source class, which is the actual data source implementation that is used when we run the app. This data source has one property, and it's called latest stock list, and it's a flow of a list of stocks. And now we want to implement this property. So what we now want to do in the data source is we now want to periodically call the mock API in order to retrieve the most current stock prices. And then we want to expose these stock prices as a flow. So let's call mock API.getCurrentStockPrices here. In order to perform this network request periodically, we can simply put it into a while true loop and then delay for 500 milliseconds. This way, new stock prices are fetched every 5 seconds. In a real-world application, it's probably more efficient to use WebSockets, or at least increase the time between network requests in such a case. But for the sake of our example here, we leave it like this. Of course, the compiler is not happy, and the IDE shows an error, since we are not returning a flow yet. So we have to do this now. But how can we actually create new flows? Let's focus on this question in the next lesson. In this lecture, you are now going to learn how to create new flows from scratch by using one of the many available flow builders. So let's directly jump into a new playground file to play around with the most basic flow builders. I already created a new package in our flow playground called builders, and in there I created the first file. Now, one of the most basic flow builders is flow of. So let's create our first flow with this builder. Okay, there is a problem. The error message, "not enough information to infer type variable t," is displayed. This means that the compiler doesn't know which type the flow should emit. So let's explicitly define that this is a flow that will emit integer values. Okay, perfect. Now the error is gone. So the compiler now knows that we plan to emit integer values. And now we can, for instance, emit the single value by passing only a single value to the flow of builder. So let's pass the integer value of 1 as a parameter. Great! We've created our first simple flow that will emit the integer value of 1. But how can we observe our new flow now? This can be done by calling a special operator, a terminal operator, on the flow. One such terminal operator is the collect operator. Of course, we will cover terminal operators in much more details later in this course. But for now, all we need to know is that you can call the terminal operator collect on the flow in order to observe the items that are emitted by our newly created flow. Collect expects a lambda function, and for this lambda function, the emitted value of the flow is the only input parameter. Let's just print out the emitted value in the lambda itself. Again, the IDE shows an error now. This is because collect is a suspend function, so we have to either call it from another suspend function or a coroutine. We will later talk about why collect is a suspend function. But for now, let's simply use the coroutine builder run blocking for the main function in order to create a new coroutine. From the coroutine that is started with run blocking, we can now call the suspend function collect, and so the compiler is happy. You know what? Actually, there is also another option instead of using run blocking here. Since Kotlin 1.3, it is possible to directly define the main function as a suspend function. So if the main function is already a suspend function, we actually don't need to create a new coroutine by ourselves anymore. So we can safely remove the run blocking coroutine builder again. Defining the main function as a suspend function is more or less the same as having a regular main function together with run blocking. However, I think that having main as a suspend function makes these small examples a little bit shorter and nicer. Alright, let's run the main function now. And as you can see, as expected, we have created our first flow that emits a single value, 1, and with collect we can observe this value, and in the collect lambda we receive this value and we print out this value, and as you can see on the right in the console, this first value, the value of 1, is printed out. Now, instead of only passing a single value, we can also pass multiple values, because there's also an overload of the flow of builder available that takes a variable amount of arguments. As you can see, this time we don't actually need to declare the flow type, since the compiler can infer the type from the values that we passed. And since they are all integers, it knows that this is a flow that emits integer values. However, sometimes it's still useful to explicitly define the type anyway, in order to make it more obvious about what type this flow emits. So let's do this here as well. Of course, if we define a flow that emits integer values, we can't simply pass values of other types, like a string for instance, to the builder. If we would do that, you can see that the compiler shows an error. In this case, we of course could change the emitted type of the flow to any in order to fix this error. But then we would lose the type safety. So let's stick to the integer flow. If we now collect the flow again, and print out the emitted values, and then run this code again, you can see that for the second flow, actually 3 items are emitted, 3 values are emitted, and for each item we call the print statement, and in the console you can see that we have this print statement 3 times. Another very simple way to create flows is to use the asFlow extension function. We can call it on collections like lists or sequences. So let's now simply create a list of 3 strings. And by using the asFlow extension function, we can convert this list into a flow. Let's now again collect the emitted values and print them out. If we now run this code again, you can now see the asFlow extension function in action. And what we did here is we converted the list of the 3 strings ABC into a flow. We collected them, and then for each emitted value, we print out asFlow and the emitted value. And you can see that the 3 letters ABC were printed out on the console. The 2 builders that we have used so far, namely flowOff and the extension function asFlow, are great. However, they are not really flexible. They simply convert a single value or multiple values into a flow. A flow builder that is much more flexible is Flow. This builder takes a suspendable lambda block, which means that we can call regular and suspend functions in there. So in the lambda, let's first call the suspend function delay and pass 2000 milliseconds to it. Now, if we want to emit a new value, we can simply call the emit function. Let's emit a new string with the value item emitted after 2000 milliseconds. And now let's again collect from the flow and print out the emitted values. And if we run this code now again, you can see that after a 2-second delay, the string that we have defined is received and printed out. So with this flow builder, we are very flexible because we can pass arbitrary code blocks that emit values to it. We can even collect from other flows in the past block and re-emit its item. So let's now collect from our second flow, the one that we created earlier, and for each emission, we simply re-emit the value. So let's run this code again. And as you can see, with the flow builder, we can collect other flows. So here we collect the second flow and basically re-emit all the emissions of the second flow. And so we re-emit and print out all the values of the second flow. Actually, there is a shorthand for this kind of collect and emit construct, which is emit all. So instead of calling collect and then re-emitting the value, we can simply use emit all. This does the same as before, but is much more concise. Of course, there are also more complex flow builders like callback flow or channel flow. But in this lecture, since we are only starting our flow learning journey, I wanted to only focus on the most simple ones. So to summarize this lecture, let's have a look at this table that shows the flow builders that we've used in this lesson. At first, we have used the flow of builder, which creates a flow from a fixed set of values. Then we use the asFlow extension function, which can be called on various types in order to convert them into flows. Last but not least, we used the flow builder flow, which is the most flexible one because it's a builder function to construct arbitrary flows from sequential calls to the emit function. Okay, so now we have all the knowledge that we need in order to create a first flow in our use case, so let's jump back to our use case in the next lecture. Alright, with our newly required knowledge about flow builders, we can now jump back to our first use case, and we should now be able to create a flow in our network stock price data source that periodically emits the recent stock price data. But what flow builder should we use here? Should we use the flow of builder or the asFlow extension function or the flow builder? Since we don't have a fixed set of values or a collection that we can convert into a flow, we need to use the flow builder, since we can pass any arbitrary code to it. In the lambda block that we pass to the flow builder, we now want to emit the list of recent stocks and their prices every 5 seconds. Therefore, let's store the list of stocks into its own variable. And then we can call emit and pass this list to it. Now, because of the while true loop combined with the delay of 5 seconds, A network request to fetch the most recent stock data is performed every 5 seconds. And every time we receive new stock data, we emit this data in our flow. Actually pretty simple, right? So now that we have properly created our flow that emits the latest stock prices, we can now observe this flow in our view model. So let's switch to our view model. Let's first add an initializer block. As you probably know, this initializer block is executed whenever a new instance of the view model is created. In this initializer block, we now want to collect from our new flow. So let's call stock price data source dot latest stock list dot collect. And for now, let's just use Timber to log out every time we receive a new item. Let's only print out the first stock of the stock list, since the list is pretty big. It contains over 6,000 stocks of companies from all over the world. Let's also rename this parameter to stock list so that this code is a little bit easier to understand. Oh, this error shows up again. As we have seen in the last lecture, the terminal operator collect is a suspend function. And in order to call a suspend function, we have to create a new coroutine. Let's simply take the view model scope and create a new coroutine with launch. To use the view model scope as a scope in which to launch a coroutine here is a good choice, since it cancels the collection of the flow when the user leaves the activity and the view model gets destroyed. We will take a look at the details of flow cancellation in the next section. If you want to refresh your knowledge about scopes in general, or the view model scope specifically, I can recommend you to take another look into section 9, which covers coroutine scopes and structured concurrency. Now when we open up logcat and run the app, and navigate to flow use cases and use case number 1 about the flow basics, you can see in logcat that the first stock is printed out. But as you can see, the first stock is not printed out only once, but roughly every 6 to 7 seconds. This is because every time we receive a response from the mock API, the data is emitted in the flow, and in the view model, we print out this new stock data. As you can see, the first item is Apple, because it's the biggest company. And if we take a look at the current price of the Apple stock, you can see that we have a random stock price in each emission. So our mock API works very well and provides us random data for every request. But why do we get a new emission only every 6 to 7 seconds? Didn't we define a delay of only 5 seconds between each emissions in our flow builder? Well, let's have another look at our data source. Indeed, we only delay for 5 seconds between each network request. However, when we take a look at the mock API behavior, which is defined in the file mock-api-behavior.kt, you can see that a delay of 1.5 seconds is defined there. So the 5 seconds of the delay plus the network request that takes 1.5 seconds explains the time of about 6.5 seconds between each individual flow emission. So this means that the interval in which items are emitted varies depending on the amount of time the network request takes. This is fine for our use case here. But later in the course, I will show you how you can call the API every fixed amount of seconds. Let's now switch back to our stock price data source. Alright, in this lecture we have put our knowledge of flow builders into practice and created our first real flow in an Android application. In the next lecture, we will work on displaying the most recent stock data list on the screen. In this lecture, we are going to show the list of stocks in the UI of our use case and update the stock prices whenever the flow of our stock price data source emits a new item. How can we achieve this? Well, it's actually pretty simple. The activity is already set up in a way that it observes the current stock price as LiveData property of this view model and renders the data that it receives accordingly. So the only thing we need to do is to set proper values for this LiveData property here. As a reminder, right now in the initializer block, we are observing the flow of the latest stock prices of our data source, and for each emission, we print out the first item of the stock list. Instead of the log statement, we can simply set the value of the LiveData property to the stock list. Oh, it seems that this doesn't work. So what's the problem here? Of course, the LiveData expects an UI state instead of the stock list. No problem. Let's create a new success UI state and pass the stock list to it. And that should be enough for now. Let's now launch the app, navigate to the use case, and then after about 6.5 seconds, the list of stocks should appear. Perfect. On the top of the UI, you can see the last update time text field, which shows the last time the UI received new stock data. And as you can see, roughly every 6 to 7 seconds, this time gets updated, and also the prices of the stocks get updated as well. So our code in the view model works fine. However, it is a bit verbose and has quite some nesting. We could improve the code here a bit by using a different terminal operator instead of collect. And this other terminal operator is launchIn. But before we use the launchIn terminal operator, I want to first talk about terminal operators in general in the next video. Let's now talk about some of the most basic terminal operators. I created a new package called Terminal Operators in the Flow Playground package, and in there I created a new file called Flow versus lists. In the main function, let's create a new flow that emits the integer value 1 after 100 milliseconds and the integer value 2 after 100 additional milliseconds. Let's also add a print statement whenever we emit a new value. So when we create a new flow with the flow builder, no code is actually executed. This flow builder here is basically just a declaration. This means that no code is executed when we only create a flow. This is different to collections, for example. So for instance, if we create a new list by using the buildList function, and also add print statements whenever we add a new item to the collection. And when we now execute this code, you can see that these print statements in the flow builder are not executed because they are not printed in the console on the right. So this means that the code in the flow wasn't executed. On the other hand, as you can see in the console, the code when building the list was executed. So a list was built and the two elements were added. So as you can see, by only using a flow builder to create a new flow, no producer code is actually executed. But when we create a collection with buildList, the builder function code is immediately executed. In fact, it wouldn't even be possible to execute the code in the flow builder, because it calls two different suspend functions, delay and emit. And of course, these suspend functions can only be called from a coroutine, but right now we are in a regular main function and not a coroutine. So this code simply can't run on its own. But how can we execute the flow builder code now? We can achieve this by calling a special operator, a terminal operator, on the flow. And the terminal operator that we already know is the collect operator. So let's copy this file and create a new file and call the new file to collect. And in this new file, let's remove the code to build the list again. And instead, let's take the flow and let's call the terminal operator collect in order to execute the flow builder code and to receive the items of the flow. And again, there is a problem and we see this familiar error message again. And it says that collect is a suspend function and we have to call it from either a coroutine or another suspend function. But why does the collect function need to be a suspend function? As mentioned before, it is possible to call suspend functions from flow builders. And so, every flow needs a coroutine in which it can be executed in order to be able to call these suspend functions. So if we want to execute the flow builder code, we need to call a terminal operator on the flow. And since every terminal operator is a suspend function, we need to call it from a coroutine. And this coroutine is also the same coroutine in which the code of the flow builder will be executed. So let's now simply use the simple coroutine builder run blocking to create a new coroutine and then collect the flow in there. And when we now run this new example here, you can see that the code in the flow builder is now executed since the two print statements emitting first value and emitting second value is printed out. The coroutine that we created with run blocking here will suspend until the flow completes. So basically when the complete flow builder code was executed. This means that if the flow actually never completes, this program here would actually never finish. So if we, for instance, add a while true loop to the end of the flow builder, and execute this example again, you can see that this program continues to run since our flow never completes. Let's now remove the while true loop again. To find out which items we actually receive, let's now add a print statement to the collect lambda. And when we now run this example again, you can see that the previous example is still running, so we have to stop this one and rerun the new one. You can see that we receive both of the emitted values in the collect block. Now, of course, there are also other terminal operators than collect available. For example, there is first, which returns only the first emitted value. So let's create a new file 3first. And instead of collect, let's call first. Then let's assign the result of the call to flow.first to a new property called item. And let's print out this item. When we now run this small example, you can see that with first we receive the first emitted value, and this value is then printed out in the console. What's interesting here is that not only is the second value not received, it also didn't get emitted, because emitting second value is never executed and never printed out. And this is because by using the terminal operator first, the flow gets cancelled once the first item got received. If the flow wouldn't emit any items, a call to first would throw a no such element exception. To avoid this, we can simply use first or null. In this case, null will be returned if the flow doesn't emit any items. Another option is to pass a predicate to first. For example, we want to get the first value that is bigger than 1. And when we execute this code now, you can see that both the first and the second value is emitted, but only the second one is received. And this is because the first item doesn't fulfill this predicate, because 1 isn't bigger than 1, and so it is discarded, but the second value is received because 2 is bigger than 1, and so received 2 is printed out. Besides first, there is also the last terminal operator, which returns the last emitted item. So let's create a new file and use last there. And when we run this main function with the last operator, you can see that only the last emitted value, so 2, is received. Of course, there's also the function last or null available, which will return null when the flow doesn't emit any values. These two operators, first and last, probably remind you of Kotlin's collection processing operators. And yes, a lot of operators that are available for collections also exist for flows. The next terminal operator that we will now take a look at is similar to first and last. It's the terminal operator called single. Let's also create a new file for this one and use it there. The single operator will return a single item, but only if one, and that means exactly one, item is emitted. So in our code here, since we are emitting 2 items when we run the code, an illegal argument exception will be thrown. This is, of course, because our flow emits 2 values. So when we comment out, for example, the second emission and run it again, you can now see that the single emission is received and printed out. Other terminal operators that are very useful are toSet and toList. Let's also create a new file for them. And let's copy this run blocking block and then use the toSet operator in the first run blocking block and toList in the second run blocking block. And if we run this example here, you can see that the toList and the toSet operators wait until the flow completes, and then they return all emitted items as a collection, like a list or a set. And as you can see in the print output, here we first receive a set with all emissions, and then we receive a list with all emissions. Operators like first or toList and toSet are very helpful for tests. The next terminal operator that I'm going to show you is fold. Let's remove the second run blocking block again, and in the first one, let's use fold. Fold expects an initial value. So let's define, for instance, 5 for it. And in the lambda that we pass, we have access to the accumulator and the currently emitted value. The fold operator is very similar to the reduce operator. And with it, we can do things like calculating the sum of all emitted items. So every time a new item is emitted, the lambda is executed, and the defined operation, in our case, adding the emitted item to the accumulator, is defined. But how does this work exactly? Initially, so for the first emitted item, the accumulator has the value that we defined for the initial value, so 5. And the value of the first emitted item is 1. For each subsequent emission, the accumulator is the result of the operation from the last lambda block execution. So the result of the first lambda block execution is 6, because 5 plus 1 is 6. When the second value is emitted, the accumulator is the value of the last execution, so 6. And the second emitted item is 2. And in the lambda, in the operation where we sum up the accumulator and the emitted item, so 6 plus 2, the value is 8. And since 2 is the second emission, the final result of the fold operator should be 8. So if we now execute the code to check if our calculation was right, you can see that we were right and we received 8 with our fold operator. As mentioned before, there's also the reduce operator available, which is pretty similar to fold. However, with reduce, you can't specify an initial value, and therefore the operator in the lambda will only be called once the second element is received. All right, now we covered all of the basic terminal operators. We needed them in order to execute a flow and to receive values that the flow emits. Let's now quickly recap which terminal operators we used in this lesson. At first, we used the simple collect operator, which receives all emissions from the flow. Then we used the first terminal operator in order to only get the first emission of the flow. Similar to the first operator is the last operator, but instead of the first item with last, we get the last emission of the flow. The single terminal operator returns a single emission of a flow, but only if the flow emits a single value. Otherwise, if the flow emits no values or multiple values, an illegal argument exception is thrown. Afterwards, we took a look at the toList and toSet operators, and these operators wait until the flow completes, and then all the emissions will be returned as a list or a set. Last but not least, we had a look at the fold and the reduce operator, and these are useful in order to perform operations like summing up all of the emitted items of a flow. These are not the only terminal operators, and in the next lesson we will have a look at another terminal operator in detail. The terminal operator that we now cover in this lesson is called launchIn, and this one is quite different to the others. I prepared a new playground file in which I already created a new flow, which does the same as the flow in the previous video. Namely, it emits the value 1 after 100 milliseconds and the value 2 after 200 milliseconds. Let's just directly call the launchIn terminal operator on our flow and open up its documentation. There, in the function definition, you can see that in contrast to the other terminal operators, launchIn is not a suspend function, but a regular one, since there is no suspend keyword in front of the function. In the last lesson, I told you something that is not fully true. There I said that every terminal operator needs to be a suspend function because then it needs to be called from a coroutine. And the flow builder code is then executed in this coroutine, and so it is able to call suspend functions like emit by itself. However, launchIn is an exception, since it is not a suspend function. Therefore, here we don't need to start a new coroutine before calling it, but instead, as you can see in the function definition, we need to pass a coroutine scope. So let's just create a new coroutine scope with an empty context. And then let's pass this scope to launchIn. Passing a scope enables the launchIn function to internally start a new coroutine in this scope and then collect from the flow. And that's the reason why the launchIn operator doesn't need to be a suspend function. It is because we need to pass a scope, and then internally the launchIn function starts a new coroutine and then collects from the flow. If we go into the function implementation of launchIn, you can see that what I just said is actually correct, because launchIn launches a new coroutine on the scope that we pass and then collects from the flow. So launchIn is basically just a shortcut for scope.launch and then collect from the flow in the coroutine. Now we have a basic idea about the launchIn operator. But how can we actually perform operations for every emitted item now? With collect, it's easy. We can simply pass a lambda block there. So let's print out whenever we receive a new item. However, when we take a look at the function definition of launchIn again, you can see that we can't pass a lambda block to it, but only a coroutine scope. So how can we perform operations for every emission in this case? Well, we need to use a new operator for that, and this one is the onEach operator. OnEach is a simple operator that can be called on the flow, and it has access to the emitted item and can perform a given action. Let's simply print out the emitted item in the onEach operator. Let's now add a thread.sleep call in the end so that this main function doesn't shut down before the flows in the coroutines get collected. And when we now run this code, you can see that launchIn and collect behave in a similar way. Both trigger the flow to emit values, so emitting first value is printed out twice, and both also receive the emitted values and print them out. So received one in collect is printed out, and received one with launchIn is also printed out. And the same thing happens with the second value. Subscribing to a flow is a little bit more readable with launchIn than with collect, since there's only one level of nesting. However, launchIn does not only provide some syntactic sugar for us. There's also a subtle difference in behavior between launchIn and collect that you should be aware of. As mentioned before, launchIn is a regular function and not a suspend function, and therefore it doesn't suspend the coroutine in which it is called until the flow has completed. On the other hand, collect is a suspend function and will suspend the coroutine until the flow has completed. So if we comment out the collect section and use a second launchIn construct after the first one, and also adjust the print statements a little bit so that we know which launchIn construct received the value, and then execute this code again, you can see that the two flows are collected concurrently, because the first emission is printed out twice at the beginning, and then the first emission is received by both launchIn constructs, and then the second emissions happen at the same time, and then the second emission is printed out in both constructs. On the other hand, if we now comment out the two launchIn constructs and instead collect the flow twice by using the collect terminal operator after one another, and also adjust the print statements again so we can differentiate the two collect calls, and then execute the code again, then the flows are collected sequentially. So the first item of the flow is emitted in the beginning and printed out by the collect lambda, and then the second item of the first flow is emitted and printed out, and only when the first flow has completed does the second flow start to emit values. As mentioned earlier, this is because collect suspends its coroutine until the flow completes. Only then can the coroutine resume and start collection on the second flow. And that explains the sequential nature of execution here. So here, we only launch a single coroutine and then collect from the flow sequentially. In the launchIn example before, we actually launched two coroutines, and these coroutines then were executed concurrently. In most use cases, you probably want to collect flows concurrently. So you will probably end up using launchIn much more often than collect. Great! In this video, we have learned the ins and outs of the launchIn terminal operator. Let's now use this operator in our first real flow use case in the next video. Alright, now that we have a pretty good understanding of terminal operators, we can now improve our code here in the view model of use case number 1. In the last lecture, we learned that we can use the launchIn terminal operator as a shorthand for this construct here, which launches a coroutine and then collects from the flow in the coroutine. So instead of this construct, we could use stock price data source dot latest stock list dot launchIn, and for the scope it makes a lot of sense to pass the view model scope. We also need to add the onEach operator, in which we have access to every emitted stock list. Let's assign the success UI state to the LiveData property here. With the second construct that uses launchIn here, we have a little bit less nesting. So by using launchIn, we have a code that is a little bit more readable than using this construct here above with collect. So let's remove the code that uses collect. And let's now run the app to verify if everything works as before. And go into flow use cases and use case number 1. And after a couple of seconds, the stock lists should be displayed, yes. And also every 6 to 7 seconds, we should receive new data. Yes, this also looks good. So our app works as before, but we have improved our code in the view model a little bit by using launchIn instead of collect. Our use case here has a small problem. When we go back again and leave the use case, and then when we open it up again, you can see that here is at the beginning no loading indicator before the initial stock data is displayed. So let's do it one more time. If we go back and open it up again, there is just a white screen, and then suddenly the stock list appears. And what we want to have here is a loading indicator. But what's actually a nice way of implementing such a loading indicator? Well, I have an idea. But before we realize this idea, we should learn a little bit about lifecycle operators for flows. There are 2 operators for Kotlin Flows that I would call lifecycle operators. And these 2 are onStart and onCompletion. With the onStart operator, we can define an action that is performed right before the flow gets collected. Let's simply log out that the flow starts to be collected. It's important to mention that the action in the onStart operator, so in our case the print statement, is invoked as soon as the collection from the flow starts, and not when the first item is emitted. The other lifecycle operator is onCompletion. And this one allows us to specify an action that is executed after the flow completes. A flow can either complete normally, so when all the values of the flow got emitted, or exceptionally, when the flow throws an exception. Let's just output flow has completed when the flow completes. In the onCompletion block, we have access to a parameter called cause, which is of the type throwable. This parameter tells us whether the flow completed normally or exceptionally. When the flow completed normally, cause is null. And when the flow completed exceptionally, cause holds the exception that was thrown in the flow. As you can see, when working with Kotlin Flow, or in a reactive programming style in general, we end up with a code style that is quite different to ordinary, imperative, and sequential code. Here, we have a kind of pipeline where each of the operators is executed one after the other. From now on, let's call such a construct a flow processing pipeline. For our lifecycle operators on start and on completion, it is important to note that these operators can be installed at any position within the flow processing pipeline. So we could also move the onStart operator to the very end, right before launchIn, and the behavior here would be actually the same. We can also define multiple onStart operators in our pipeline. For example, we can have one onStart operator in the end and one at the beginning of our pipeline. Let's also adjust the print statements a little bit so that we can differentiate between those two. And when we now run the app and navigate to the first use case, and then open up logcat and filter for the log messages, you can see that the code in the onStart blocks was executed when the flow started to be collected. What's interesting here is that the code in the second onStart block was actually executed before the one before. The onCompletion block is not executed, since we basically have an endless flow which never completes, because we have a while true loop in the flow and it emits a new stock list every 6 to 7 seconds. What's also interesting to note is that we can call emit in the onStart and onCompletion blocks in order to emit new items to our flow processing pipeline. Let's now talk about two important terms for flow processing pipelines: upstream and downstream. Let's have a look at the onCompletion block here, for example. Every operator that happens before this block is the upstream for this block, and every operator that is executed afterwards is the downstream for this block. If we now want to emit a new item in the onCompletion block now, for example, a new stock list, we can simply call emit there and, for instance, simply emit an empty list. And this now means that the item is emitted downstream to the next operator below the onCompletion block. And this one is the onEach operator. We will talk about operators that only affect the upstream of the pipeline, like for instance the flow on operator, later in this course. Most operators, though, only affect the downstream. Let's now do something that is actually useful. Our initial goal was to show a loading indicator when the user opens up the use case. onStart is the perfect lifecycle operator for this. So we don't need an onCompletion block, so let's remove it again. and also remove the second onStart block, and also remove the print statement in the first onStart block. In order for the activity to show a loading indicator, we simply need to set the UIState.loadingState to our LiveData property. So let's emit the loading UIState in our onStart block. The next operator downstream, so the onEach operator, won't receive a list of stocks anymore, but instead it will now receive an UIState. So let's adjust the code accordingly. However, there is an issue. Android Studio tells us now that we need to emit a list of stocks instead of an UIState. Why is that? Well, let's take a look at the documentation of the onStart operator. onStart is an extension function on a flow that emits the generic type T. And this flow on which the onStart operator is called on is also called the original flow. In our action block, we can operate on a flow collector with type T. With a flow collector, as you can see in its interface definition, we can emit new values that need to be of that type T. Let's go back to the documentation of onStart. The action block operates on a flow collector with type T, and therefore we can only emit this type T, which is the same type that the original flow emits. And since the original flow in our flow processing pipeline is the latest stock list flow of the stock price data source, we can only emit stocks here in our onStart operator and not an UIState. So we somehow need to call onStart on a flow of UIStates instead of on a flow of stocks. And how can we do that? Maybe we can use an operator that we already know, the onEach operator, to convert a flow of stocks into a flow of UIStates. Well, convert is not really the right word for this. What flow operators actually do is they perform an operation and then they return a new flow. So we need an operator that returns a new flow that emits UIStates. So let's just try to use onEach before onStart, and let's try to emit UIState.success from it and pass the list of stocks. However, this doesn't seem to work. Let's have a look at the documentation of onEach to find out what's the problem here. onEach is an extension function on a flow that emits the generic type T. But it also returns a flow of that type T. So we can't create a flow that emits a different type than the original flow with onEach. onEach can actually only be used for side effects. It doesn't manipulate the stream of items. But we can trigger some other actions with it, like setting the LiveData property, like we do at the end of our pipeline here. What we need is an operator that can return a flow that emits a different type than the original flow. So the return type of this operator must not be T, but some other generic type. When thinking about this, the operator map, which most people probably know from collection processing, comes to mind. Let's see if this operator is available for flows as well. Oh yes, there it is. Let's have a look at its documentation. The documentation says, returns a flow containing the results of applying the given transform function to each value of the original flow. So this sounds promising. And indeed, the type that the returned flow emits, namely the type R here, is different than the type T of the original flow. So with map, we are now able to pass a transform block that receives a stock list and transforms it into an UI state, and then emits this UI state to the downstream. Oh no, there is still a problem. The receiver in onStart, as you can see in the IDE hint here, is UIState.success. So we need to cast the success UI state in the map operator to the UI state supertype. I'm not sure why Android Studio makes this cast gray to indicate that this cast isn't needed, since it definitely is needed. But anyway, now our feature should now show a loading indicator, and let's check if this really works. So we have launched the app again, and when we open up the first use case, you can see that perfect, the loading indicator shows up, and when the first stock list is emitted, the list of stocks is then received. So let's try it again. Enter the use case. Here it is, the loading indicator. So in this lecture, you learned about the lifecycle operators on start and on complete. And in the next lecture, you will see how we can improve our view model code here even further. All right, in this lecture, we are going to improve the code of the view model even further by using the asLiveData terminal operator. In fact, our code here in the view model in this current state actually has a very big problem. To illustrate why there's a problem, let's switch to our stock price data source. And here, let's use Timber to log out fetching current stock prices whenever the data source performs a network request in order to retrieve the current stock prices. I'm using the tag flow here for this Timber log message so that we can later better filter our log messages with logcat. So with this log statement here, we can then, when we run the app, check if this data source is still active and is still fetching stock data from the network and emitting them to the flow. So if we now run the app and open up logcat and filter for flow, and then when we switch to the app and navigate to the first use case, you can see in logcat that the data store starts to fetch stock prices, and every 6 to 7 seconds a new line is logged out. Now the problem that we currently have is that even when we put the app into the background, so when we put it into the background, you can see in logcat that still new log lines are printed out. So the data source is still fetching new stock prices from the network, which is a problem. And that's not only a small problem, but a very big one, because these network requests cause unnecessary loads to the servers. Additionally, they also waste a lot of resources on the device of our users. and we definitely need to avoid this. What we need to avoid is to have such a infinitive flow that never stops, but instead what we need is a flow that stops when the app is in background and restarts again when the app comes back into the foreground. So let's now switch to the view model, and our goal now is to cancel the flow when the app gets into the background. A first naive solution would be to simply create a new job property. And then assign the job to the job that the flow pipeline with launchIn returns. Let's move this assignment into its own function. And also create another function called stopFlowCollection, in which we cancel the job, which leads to the cancellation of the flow. Let's now remove the private modifier, and also we remove the initializer block. Let's also define the stock price data source as a property, so that we can get rid of this parameter here in our start flow collection function. Alright, this is the naive solution of the view model. In the view model, we now have two functions, one function to start the flow collection and another function to stop the flow collection. And what we need now is to switch to the activity, and in the activity we need to override the onStart lifecycle function. And in there, let's call viewModel.startFlowCollection and also override the onStop lifecycle function. And in there, let's call viewModel.stopFlowCollection. So now when the activity starts, we start the flow collection, and whenever the activity goes into the background, the onStop function is called, and then we call viewModel.stopFlowCollection. And this should accomplish our goals to stop the flow when the activity goes into the background, and when it comes into the foreground, the start flow collection should be triggered again, and then we should receive stock prices again. One thing we should do additionally is to go into the view model again and add an onCompletion block. And in the onCompletion block, let's add a timber log statement in which we simply log out when the flow completes. This way we can check then in logcat if the flow was actually cancelled. So let's now restart the app. And when we now open flow use cases, use case number 1, you can see that the data store starts to fetch the stock prices every 6 to 7 seconds. And once we click on the home button to put the app into the background, you can see that flow has completed, is printed out. So indeed, our data source stops its work. There are no more network requests performed, but instead the data source is inactive and no device resources are wasted. If we put the app in the foreground again, you can see that now new stock prices are fetched and emitted, and here again, and our UI also updates every 6 to 7 seconds, so the app works as desired. So this naive solution here works as expected, however it has two big drawbacks. And the first drawback is that a lot of boilerplate code is needed. So in the view model, we need this additional reference to the job, and we need these two functions, start flow collection and stop flow collection. And we need to assign the pipeline to the job. And that's all a lot of manual work to do that's error prone and can easily lead to errors. And not only code in the view model is needed, also when we switch to the activity, we need to call start flow collection in the onStart method, and in onStop we call stop flow collection. So a lot of boilerplate code, and that's obviously really bad. The other big problem here is that whenever there's a configuration change, the flow gets cancelled. And that's actually not what we want. So if there's a configuration change, so for example, when the user changes the device orientation, or when the user switches the app to multi-window mode, or for example, when the user switches from dark to light mode, then the activity is recreated. And whenever this happens, right now, our flow is cancelled, and a short period afterwards restarted again. And we actually want to avoid this cancellation and this immediate restarting of the flow. So to demonstrate this, when we, for example, just change from light mode to dark mode, then you can see visually nothing changes because we haven't adjusted our app based on light mode or dark mode. But on the other hand, in Logcat, you can see that the flow was cancelled because the activity was destroyed, and shortly afterwards it was recreated, and then the flow was restarted. And this restarting should be avoided, and what would be better would be that the flow isn't even cancelled but continues to run in situations like configuration changes. So we need a better solution here. Okay, I reverted the changes of our previous solution again. And now I want to show you the proper solution. And this one can be achieved by using the asLiveData terminal operator. So instead of launchIn, we can use asLiveData. And what this new terminal operator allows us is that it directly converts a flow into a LiveData object. Since LiveData is a type of the Android X lifecycle library, the asLiveData terminal operator is not defined in the Kotlin X coroutines library, but in the Android X lifecycle library as well. Well, to be precise, the library is called Android X Lifecycle LiveData KTX. And since we have already added this dependency in our build.gradle file before, we are ready to use it. So let's now switch back to the view model. And let's first open up the official documentation of the asLiveData operator to find out about what this operator is all about. The documentation says that it creates a LiveData that has values collected from the origin flow. So as you can see, asLiveData is an extension function on a flow, and it returns a LiveData with the same type as the type of the flow on which it is called on. So it has the same type as the origin flow. In our view model here, the origin flow is the one we get from the latest stock list property of the data source, which is a flow of a stock list. However, the map operator returns a new flow that is a flow of UI states, and therefore asLiveData creates a LiveData object that emits UI state objects. Now, Since we get a LiveData object directly from the call to asLiveData, we can directly assign the pipeline to the current stock price asLiveData property. So we can remove the initializer block and directly assign it. Since asLiveData returns a LiveData object and not a mutable LiveData object, we switch the type here. And there's also an error here in the onEach block where we want to set the value of the LiveData object to the emitted UI state, but this is not possible anymore because now this LiveData property is a LiveData object and not a mutable LiveData object, and so we can't assign new values to it. In fact, with asLiveData, we don't even need to manually assign UI states to this property, since that's what's basically the asLiveData operator is doing, so we can remove the onEach block altogether. So to sum it up, the asLiveData terminal operator is called on a flow, in this case on a flow of UI states, and converts this flow into a LiveData object that emits UI states. Now our code looks very short and nice, or what do you think? Let's now verify that this code is not only beautiful, but also functional, and it is doing what we want it to do. Therefore, let's again add an onCompletion block to see if our flow actually gets cancelled. And let's now run the app. And when we now navigate to the use case, you can see that logcat prints out that the stock prices are fetched, so the data source becomes active. And when we now put the app into the background, you can see that after about 5 seconds, it will print out that flow has completed. And I will tell you later why this is 5 seconds after we put the app into the background. When we now bring the app into the foreground again, then yes, the data source should become active again and network requests should be happen now again. And as you can see in logcat, this is the case, and we get new data and new stock prices are then displayed within the app. The asLiveData terminal operator is, when we compare it to other terminal operators like collect or launchIn, a bit strange. For the other terminal operators, we had to either start a new coroutine, as it was the case with the suspend function collect, or we at least had to pass a scope, like for instance with launchIn, so that launchIn can then internally start a new coroutine. However, here with the asLiveData operator, we don't need to do any of these two options. We don't need to create a coroutine, but we also don't need to pass a scope. So how does asLiveData work? Let's have a look at the internals of asLiveData to find out more. So I press the Command key, and when I then click on the asLiveData operator, I get into the implementation, and here you can see that it uses the LiveData builder. And to the LiveData builder, it passes this block here, where it collects from the origin flow and then emits this value to the LiveData property. So here, this emit means that it doesn't emit to a flow, but it emits a new value to our LiveData property. When we now take a look at the LiveData builder function here, you can see that this one returns a coroutine LiveData object. And when we have a look into such an object, when we scroll down a bit, you can see that In this coroutine LifeData object, a new scope is created, a new coroutine scope is created with the dispatchers.main.immediate dispatcher and also some other context elements. And this scope is then passed to a so-called block runner. When we search for the block runner where it is used, you can see that whenever the LifeData object gets active, so when in our case, when the activity that observes the LifeData object gets into an active state, the block runner.maybeRun function is executed. On the other hand, when the LifeData object gets inactive, so in our case, when the activity goes into the background, the block runner is cancelled. Let's now have a look at the maybeRun function of the block runner. And here you can see that a new coroutine is created, and in there the block is executed, which we saw before, the block that collects from the origin flow and emits these items to the newly created LifeData object. So to sum up what's happening inside the asLiveData terminal operator is that we don't need to pass a coroutine scope, but instead this scope is created internally. It's based on whether the LifeData is active or not. On this scope, a new coroutine is launched, and in this coroutine, the actual collection happens. But let's switch back to the view model now. Let's have another look at the asLiveData documentation. As you can see, we can pass two different parameters here, a coroutine context and a timeout in milliseconds. The context that we can pass here is passed to the coroutine scope that is created internally, and this is the one that we have seen before. And with this parameter, we are able to override the context elements by passing our own context here. So what we could do now is to pass a different dispatcher, for example the default dispatcher, to it. And this now overrides the internally used context, and therefore the default dispatcher will be used to collect the items instead of the main dispatcher. So this now means that the whole flow, so starting from the flow builder code, but also the code that happens in the operators, will be executed on the default dispatcher. But this is not needed in our case here, so let's remove this parameter again. The second parameter that we can pass to the asLiveData operator is the timeout. As you saw earlier, the flow collection was not cancelled immediately after we put the app into the background. Instead, the asLiveData operator waits for this specified timeout after the LifeData observer gets inactive, and only then cancels the flow. This behavior is necessary so that when configuration changes happen, so when the observer is in the inactive state only for a very short time, we don't need to cancel the flow and then restart it again. And with this timeout parameter, we can adjust the behavior. However, in most cases, the default timeout of 5000 milliseconds should be fine. If we would set the timeout in milliseconds to 0, we would have the same behavior here as with our first solution that we had before, which means that as soon as an orientation change happens, the flow would be cancelled, and then a couple of milliseconds later, the flow would restart again. But in our case here, by leaving the timeout to the default value of 5 seconds, the flow is cancelled 5 seconds after the observer gets inactive. So when the configuration change happens, the flow stays active and is not cancelled. And that's exactly what we wanted to achieve. I can also show you this behavior when we run the app. And when we go into the use case, and then the data source is active, and when we only do a configuration change, like for example changing from light mode to dark mode, you can see that this on completion block is not executed because the flow does not get cancelled, but instead it continues to run. Only if the LiveData observer is inactive for 5 seconds, then the flow is cancelled. So when we click the home button to put the app into the background and wait for 5 seconds, then flow has completed is printed out. All right, great. In this lecture, you learned all about the asLiveData terminal operator, and our code looks pretty nice now and works properly without big problems. When we take a look at the flow processing pipeline here in our view model of use case number 1, you can see that at the top we have our initial flow, the latest stock list flow that we get from the stock price data source, and then some operators are applied on it. In the previous lecture, we already covered the lifecycle operators on start and on completion. There, you learned that these operators are only called once at a certain point within the lifecycle of the flow. We also already talked about terminal operators, which are located at the very end of a flow processing pipeline. No code of a cold flow is executed unless such a terminal operator is applied on a flow. Besides lifecycle operators and terminal operators, there is also another category of operators, which are called intermediate operators. These intermediate operators are executed for every emission of the flow and return a new and transformed flow. We are already using such an intermediate operator in our view model here, and this is the map operator. In our code here, map is applied on a flow of stocks. So it takes a stock list, maps it to a UI state, and then returns a transformed flow that emits UI states. In this lecture, we are now going to have a look at some of the most common intermediate flow operators. Some will be familiar to you, since they also exist as collection processing operators. I already created a new file in our playground that's called one_map.kt. And in there, I created a new suspending main function in which a new flow is created. And in the collect lambda, we simply print out the collected values. The operator that we're already using, map, is pretty straightforward. We can apply it on our flow of integer values here. And we can, for instance, multiply every received value by 10. When we now execute this code, you can see that map is executed whenever it receives a new emission from the upstream flow. And therefore, in the collect lambda block, we receive the result of the initial values, which got multiplied by 10. So in the console, we can see that 1 multiplied by 10 is 10, 2 multiplied by 10 is 20, and so on. The returned flow of map can emit a different type than the origin flow on which map is applied. Therefore, we are not limited on only returning integer values, but we could also return other types, like string, for instance. So we could return a string with the value emission and then the value. And as you can see as a hint in Android Studio, collect will now receive string values. And when we run this code again, you can now see that the strings are collected and printed out. So now we get emission 1 and emission 2 and so on. As you can see, a common use case for the map operator is to convert an object into an object of another type. A very good resource that illustrates the behavior of different flow operators is flowmarbles.com. On this website, you can switch between different operators on the right-hand side. So if we take a look at the map operator, for instance, you can see that we have a nice diagram with these colored marbles. Every marble at the top represents an emission of the original flow, so emissions of the values 1, 2, 3, 4, 5, and 6. Below, you can see the operator that is applied to the origin flow. In our case, this is the map operator, and to map, the following block is passed, where every emission is multiplied by 10. Finally, at the bottom, every marble here represents the emission of the flow that the map operator returns. So for the emission 1 of the original flow, the resulting flow returns 10. If you have a hard time understanding a certain flow operator, I would suggest that you open up flowmarble.com and play around with the operator. It's also worth mentioning that you can move the marbles of the origin flow, and by moving the marbles to the left or to the right, you can see that we can change the time when the emission of the origin flow happens. But let's go back to Android Studio now. Besides map, there's also the map not null operator. This operator not only maps a certain emission, but also filters out null results. So map not null will never return a nullable type. Another simple intermediate operator is filter. So let's copy the current file and paste it here as to_filter. And then instead of map not null, let's use filter. For filter, we can now pass a predicate. For instance, we can say that every element needs to be bigger than 3. And the filter operator now filters out every emission where the predicate is not true. So collect will only receive emissions that are greater than 3. So if we execute this code here, you can see in the output that indeed only 4 and 5 is collected and both values are greater than 3. Another option would be to use filter not, and what filter not is doing is that it filters out all emissions where the given predicate is true. And what filter not is doing is that basically it only returns emissions where the predicate is actually false. So when we run the code again, you can see that we only receive emissions where this predicate is false. So only emissions where emission greater than 3 is false. Another variant of the filter operator is filter not null. Filter not null returns a flow that contains only values of the original flow that are not null. The last filter variant that I'm going to show you is filter is instance. Here, we can filter for certain types, for in our case, let's say integer, and filter is instance will now filter out every emission that is not of the type integer. In our case, since the origin flow only returns integers, this operator here will filter out basically nothing. But in cases where you have a flow that emits different types, filter is instance can be very useful there. The next two operators are called size limiting operators. And the first one that I want to discuss is called take. So let's create a new file and call it 3take. And instead of filter is instance, we use take. And as you can see, for take, we can pass a count parameter. So here we could pass, for instance, 3. And what take now does is that it cancels the execution of the flow when this passed count limit is reached. So take will return a flow that takes only 3 emissions of the origin flow. So when we run this small code example here, you will see that indeed only 3 emissions are taken and basically forwarded to the collect lambda. A small variation is take while, where we can pass a predicate. So let's again pass the predicate where it is bigger than 3. And what this will do is basically does the same as count, but with this take while we can pass a predicate and are basically much more flexible. So we can define a much more sophisticated logic here than just taking a certain number of emissions. That's strange, nothing is printed out. So as you can see, I made a small mistake. I defined basically that emissions should be taken as long the emissions are bigger than 3. And since the first emission is already smaller than 3, then the flow already got cancelled and therefore we have no output. So if we say now as long as it is smaller than 3, and execute the app again, then it should work properly. And yeah, indeed, both emissions that are smaller than 3 got printed out, and then the flow was cancelled. Now you might wonder what's actually the difference between take while and filter. The big difference is that filter does not cancel the upstream flow. Filter will just take a look at the emissions that it receives and filter the emissions accordingly. On the other hand, for take while, once the predicate is false, the upstream flow will be cancelled and no more emissions will be forwarded. The other size limiting operator is drop. So let's create a new file for drop. And instead of take, we can now use drop. And again, here we can pass a count parameter. And when we here specify 3 and execute this code, you can see that drop basically drops out the first 3 emissions. So 1, 2, and 3. And only after the first 3 emissions, the return flow will emit all subsequent values. So in our case, 4 and 5. One common use case for drop is to use drop with the count value of 1. And in this case, you're basically not interested of the first value, of the initial value, but you're only interested in all subsequent values. Similar to take while, there's also drop while, and similar to take while, you can pass a predicate here. And here we can say as long as the emission is smaller than 2, we want to drop each emission. So when we execute this app, for every emission where this predicate is true, so for 1, this emission will be dropped. So because 1 is smaller than 2, 1 will be dropped and is not printed out. But 2 smaller than 2 is actually false. And therefore 2 is forwarded and printed out. And also the same for 3, 4, and 5. The next operator is the transform operator. For transform, we can pass a transform block, but the big difference here compared to map is that, as you can see in the Android Studio hint, for transform, we have a flow collector as a receiver. And this means that we can call emit here in the transform block. And here we could, for instance, emit the received value times 10. And when we execute this code, you can see that we now get every value of the origin flow times 10. You might now wonder what's the big difference between transform and map, because with map we had basically the same result. But the big difference is that we can not only emit a single value for each value that we receive, but multiple values. For example, we can emit the unmodified received value and then the received value times 10. And when we execute this snippet again, you can see that the original value is printed out, then the original value times 10, then number 2, so the unmodified value 2, and then the modified value 2 times 20, and so on. Another intermediate operator is with index. So let's create a new file, 6 with index. Instead of transform, let's now use with index. And with index returns a flow that wraps each element into an indexed value type. So if we execute the with index example, you will see that the indexed value object is printed out. And as you can see, the indexed value object contains the index and the actual value of the emission. Last but not least, we have the intermediate operator distinct until change. So let's create a new file, distinct until change. And use it here. And what this operator now does is that it filters out values in situations where the previously received emission has the same value. So for example, when we have emissions of the same value, here like 1 and 1, and we execute this code, then you can see that the second equal emission, the second subsequent equal emission will be filtered out. So instead of 2 1 values, we have only one value. And as you can see in the end, if the 1 comes at a later point, so if it's not a direct subsequent emission, then it will be forwarded anyway. So yeah, distinct until change is also an operator that is very useful. All right, now we covered all of the most common intermediate operators. An exercise is waiting for you in the next lecture where you can play around with these operators by yourself. So have fun. In this first exercise of the flow part of this course, you now have the chance to verify if you're able to put your newly acquired knowledge about the basics of Kotlin Flows into practice. I already prepared the foundation of use case number 2. Every component, like the activity or the data source of this use case, except for the view model here, are already implemented. And your goal now is to implement the current stock price asLiveData property in the view model. When we take a look at the stock price data source, you can see that this data source is the exact same one that the one we used in use case number 1. It also provides stock data of the biggest companies in the world. Let's go back to the view model, and here in this exercise we of course want to fake the stock data a little bit. So the goals for this exercise are written as comments here in the view model, as you can see here. Let's go through the goals one by one now. Your first task is to only update the stock list on the screen when the Alphabet or the Google stock has a price that is greater than 2,300. You can find the Google stock if you search for a stock that has Alphabet Google as the value for the name property. The reason for this task is of course that we don't want to show our users that the stock of our beloved company Google is performing bad. The second goal of this exercise is to only show stocks of the United States. So only stocks where the country property has the value United States. The next task is to show the correct rank within United States and not the worldwide rank. So what is the rank? If we have a look at the app of use case number 1, you can see that, for example, Saudi Aramco is a company that is not from the United States. And if we now would filter out Saudi Aramco, then the rank would stay the same for Apple and for Microsoft. And then in the first place, we would have Apple with a rank of 1, which is fine. But Microsoft would have a rank of 3, and it should be 2 instead. So for this task, it is necessary to adjust the rank property of each stock. The next goal is to filter out Apple and Microsoft, so that Google is the number 1. Step number 5 is to only show a company if it is one of the biggest 10 companies of the United States. So when the rank property is smaller than 10. So in this use case, we then don't want to show a big list of companies, but only the top 10 company of the United States. The next goal is to stop the flow collection after 10 emissions from the data source. So the flow of the data source should not run forever, but should be cancelled after 10 emitted values. Task number 7 is to log out the number of the current emissions, so we can then check with logcat if the flow collection indeed stops after exactly 10 emissions. And finally, we want to perform all flow processing on a background thread. In this exercise, we are doing some filtering and mapping. And so it's a good practice to do this on a background thread instead of the main thread. If all of these 7 goals are achieved, the solution should look like the app that you can see on the device now, where only the 10 biggest companies of the United States are displayed, and Google is obviously leading the field. I wish you a lot of fun with this exercise. I hope you had some fun with this exercise and were able to achieve some or even all of the defined goals. In this lecture, I'm now going to tackle this exercise together with you. Let's first set up the basic flow processing pipeline and then focus on the goals. We want to get emissions from the stock price data source, and the flow property is called latest stock list. In order to convert this flow to a LiveData object, we now have to use the asLiveData terminal operator. Since we want to create a LiveData object of UI state, but right now we have a LiveData object of stock list, let's now use the map operator in order to convert the stock list to the UI state success type. Let's also use the onStart operator and emit the loading UI state when the collection of the flow starts, so that the progress indicator is shown. Great! We now have the basic setup of our flow. Let's now have a look at our goals. The first goal is to only update the stock list on the screen when the Alphabet Google stock has a price that is greater than $2,300. For this goal, I think the best operator is the filter operator, and we receive a stock list from the upstream here. And now in the filter operator, we need to filter the emissions. So first of all, let's create a new variable called Google price. And in order to find the Google price, we first have to call find on the stock list. And here in the Lambda, we get each stock. And we want to find the stock that has a name that is Alphabet Google. So find here gives us the Google stock, but we don't really need to check the stock. We only care about the current price. And now for the result of the Lambda, the actual predicate is that the Google price should be bigger than 2,300. So there's one problem here. So with find, it could be the case that we can't find a stock with this name that we have specified, and therefore we could have null here. And so we need to care about null safety here. So we could either just say the compiler that we're sure that the stock is always there, or we can be on the safe side and use the safe call operator. And when the Google stock for some reason can't be found, we just return false. So in this case, every emission that has no Google stock in it will be filtered out. Our next goal is to only show stocks of United States. So only show stocks where the country has the value United States. So intuitively, we probably think that the filter operator is appropriate here as well, right? But that's actually not true, because we don't want to filter individual emissions, but instead we want to filter the stock list itself. We basically want to take every emission, but for the stock list that is emitted, we want to apply some mapping, and in the mapping we want to filter out all stocks that are not from the United States. So let's use the map operator, and we also get a stock list from the upstream. And in the map operator, we call filter on the stock list to filter the stock list. And we only want to have stocks in our stock list where stock.country equals United States. Our next task now is to show the correct rank within United States and not the worldwide rank. And in order to achieve this goal, we have to adjust the rank of each stock in the stock list. And therefore, we can use the map operator here again. We also get a stock list here from the upstream. And since we get a list of stocks and not a mutable list of stocks, we have to use stock list.map here and create a new stock list with adjusted ranks that the resulting flow will return. So in the map operator, we have access to each stock, and in order to adjust the rank, we cannot just call stock.rank and modify this value because rank is a val and therefore we can't change it. So instead we need to create a whole new stock object, and we can achieve this by calling stock.copy, and here we can provide another rank. But now the question becomes, what is the correct rank here? And the solution is to actually use map indexed instead of map. And with map indexed, we not only have access to the stock, but also access to the current index of the stock in the list. And so we simply can set the rank to the index, and then it should be fine. Well, not completely, because we have to use +1, because the index here starts with 0, but in our UI we want to start with a rank of 1. The next goal is to filter out Apple and Microsoft so that Google is number 1. So here again, we don't want to filter individual emissions, we just want to filter the stock list of each emission. And therefore we can use the map operator again, where we once again get a stock list. And here it's pretty straightforward. We will use stock list.filter, and here we get a stock, and we basically say to the filter predicate that we want to only have stocks where stock.name is not Apple and stock.name is not Microsoft. As you can see, we have a lot of map operators applied one after the other here. And this is actually not really necessary. So we could have a single map operator where we have all this logic combined in one. This would be a bit more efficient because not as many flow objects would need to be allocated, because each applied map operator creates a new transformed flow. However, I wanted to separate the logic of each goal a little bit, and therefore I will leave it in their own map operators. In general, I think it's better to focus on readability anyway, instead of being a tiny little bit more efficient. So in my opinion, readability is most often more important than efficiency. The next goal is to only show companies if it is one of the biggest 10 companies of the United States. So only show companies where stock.rank is smaller or equal than 10. Here once again we can use the map operator, and for the stock list that we get from the upstream, we can simply call stock list.filter, and for the stock in the predicate we can simply say we only want stocks where the rank is smaller or equal than 10. Our next task is to stop the flow collection after 10 emissions from the data source. For this, we can use the size limiting operator that is called take. And we can use take simply at the beginning because we only want to take 10 direct emissions from the data source. And so let's use 10 as the count values. And this way, after 10 emissions, the upstream flow will be cancelled. And after 10 emissions, we don't get any more values. The next goal is to log out the number of the current emissions so that we can check if the flow collection indeed stops after exactly 10 emissions. So whenever we use logging, the flow itself is not transformed because logging is just a side effect, and therefore it makes totally sense to use the onEach operator. We use it at the very beginning of the flow since we want to log out when an emission is processed right away. But how do we actually get the number of the current emission here? The answer is to use withIndex. And with this flow intermediate operator, we get not a stock list in the onEach block, but an indexed value which wraps the stock list. Since we now have the indexed value in our onEach operator, we can simply log out processing emission and the indexed value. And from this indexed value, we have the value itself, so the stock list, but here we want to use the index. Again, the index starts with 0, but to have a nicer log output, we would want to start with 1, and so let's add 1 here. As you can see, there are some errors in the downstream now, and this is because the withIndex creates a resulting flow that emits indexed values. However, the operators below expect stock lists, and therefore we have to use the map operator and unwrap the indexed value again by simply mapping it to indexed value dot value again. So then the downstream again gets the unwrapped stock list. Finally, our last task is to perform all flow processing on a background thread. And this one is pretty easy to achieve. We can simply pass dispatchers.default to the asLiveData terminal operator. Well, actually, we don't want to pass the dispatchers.default hard-coded value here, because if we scroll up, you can see in the constructor we have the default dispatcher as a dependency. So let's use this dependency here as well. And this has the big benefit that in tests we can then swap out the default dispatcher with an actual test dispatcher. And this enables testing then. All right, I think we are done. Let's check out if we achieved all of our goals. So let's open up flow use case number 2. And the loading indicator shows, which is nice. And then we have a list of stocks, and all of them are from the United States. However, I think there's a small problem because the rank doesn't start with 1 but with 3. So let's have a look what's the problem here. So the problem is that we actually evaluate the rank before we filter out Apple and Microsoft. And that's the issue that we have. So we want to filter out Apple and Microsoft before adjusting the rank. And then when we run the app again and open up the second use case again, you can see that now it looks good. We have our Google stock at the top where it belongs. And then we have the other 10 companies from the US. When we take a look at logcat, you can see that we correctly print out the emissions and their number. And as you can see, after 10 emissions, there are no more print lines anymore. And this means that the flow is stopped after 10 emissions, so our code works fine. So once again, I hope you had fun with this exercise and you could put your newly acquired knowledge now into practice. And in the next lecture, we are going to recap everything that we've learned so far in our first flow section. So in this first module of the flow part of this course, we covered all of the necessary basics about what Kotlin Flows are and when and how to use them in real-world applications. Let's now recap these basics. At first, you learned that a flow represents a stream of values that are computed asynchronously. For the rest of the module, you learned the in and outs about all the components of which a flow consists of. When collecting from a flow and applying various operators on it, the resulting code looks kinda like a pipeline. At the beginning of the pipeline, there is the actual flow that we want to collect from. A flow can be created by using a flow builder. In our example use case, we used a flow builder to create a flow that hits a network endpoint every 5 seconds and then emits the result. We used the flow builder here, but there are also other flow builders available, like flow-off and asFlow, which can convert a fixed set of values or a collection into a flow. Then we had a look at lifecycle operators. These are called only once at a certain point within the lifecycle of a flow. There is this onStart lifecycle operator that we used in our use case, and this one is called whenever the collection of a flow starts. In our use case, we used it to emit the loading UI state so that the activity shows an loading indicator before the first emission of the stock list is received. Besides onStart, there's also the onCompleted lifecycle operator, which is called when the flow completes either successfully or exceptionally, or when the flow gets cancelled. Next, we covered the topic of terminal operators, which are needed in order to start the collection of the flow. Terminal operators are applied at the very bottom of the flow processing pipeline. Collect is the basic terminal operator, which simply starts the collection of the flow. All other terminal operators are built on top of collect. Other terminal operators are first, last, and single, which, as the names say, only collect the first, the last, or the single emission. Then there are the two operators toList and toSet, which wait until the flow completes and then convert the emitted items into a list or a set. There's also the launchIn terminal operator, which is basically a nicer way of collecting from a flow, since with launchIn we don't need to start a coroutine by ourselves, but we only need to pass a coroutine scope, which leads to a more readable code because there's a little bit less nesting involved. Finally, there's also the asLiveData terminal operator, which converts a flow into a live data object and is very useful in view models. We also covered the most common intermediate operators. Intermediate operators are called for every emission. Map is such an intermediate operator, and it's used to modify an emission or to convert an emission from one type to another, like we did in our use case here. Other intermediate operators are filter, which allows us to ignore certain emissions of a flow. And then there are also the size limiting operators like take and drop that we can use whenever we are interested only in a certain number of emissions. And also there's the transform operator, which is useful whenever we want to emit multiple values from the operator. And another such a intermediate operator is with index, and this one wraps the emission in an indexed value type that holds the index of the emission as well as the actual value of that emission. Last but not least, we had a look at distinct until changed, and this one can be used to filter out subsequent emissions that are equal. With all this new knowledge from this module, we were able to create a nice stock live tracking app that creates a flow, collects from this flow, and applies some operators on it to only show the live stock prices of the 10 biggest stocks of the United States. And that's it for this module. Now that we covered the basics of Kotlin Flow, we can tackle more sophisticated topics in the next modules. See you there. So if you want to dive deeper into coroutines and flow, then I can highly recommend my complete course that contains everything to fully understand and successfully use coroutines and flow in your apps. We will together create a stock live tracking app that uses flow extensively. You will also learn about state flows, shared flows, channels, and many other topics. You can find a link to the course in the description, and I would love to have you on board.